last speaker for this session, Professor Fabiano Santos. He is going to present entanglement island and page curve in the framework of Horndeski gravity. Okay, it's your
Hey,
turn.
good morning, everyone. Thanks for the invitation again. Let me share my screen. Can you see my screen?
Yes, we can.
Okay, thanks. Okay, thanks for the presentation about myself. Um, I will talk about entanglement, island, and page curve, the framework of Horndeski gravity. And then I will give some motivation why considering this topic in Horndeski gravity. Uh, Summary, this topic is an extension of the ADS-PCFT correspondence to the framework of Horndeski gravity, where we include boundary Lagrange density. Okay, this card summarize uh, the main points of my work, where I show that the the relation between the entanglement entropies for the hard models and surface in the context of Horndeski gravity for the entanglement island in the framework of Horndeski gravity, and why to compute the entanglement island in the framework of Horndeski gravity. And then with this, we can analyze the page curve and see what happened and if the unitary is preserved. Okay, the islands are regions in space-time that contribute to the entanglement. And with this, we can to assess and try to connect the region before the horizon of the black hole and the region after the horizon of the black hole, where we have the rock and radiation region. Okay. Uh, this diagram illustrates our work in general. And here we have the region after the horizon of the black hole, before the horizon of the black hole. And here we have the other region after the horizon of the black hole. And from the viewpoint of the classical way without uh, the double holographic model, these two surfaces are not connected. And recently, the professor Lisa Randall, together with Chang and Karsh and others, provide a work where it's possible. We connect these two regions or surface, if you prefer to call, where the connection between these two regions can be do using the island surface. And then this island emerge in the context of the black hole evaporation. So, in this context, and this idea is a manifestation of the ER equal to EPR. Okay, but how we can to introduce this framework in Horndeski gravity? This is the work that I published recently together with Pena and Saridaspis and other friends. In this cartoon, we have an illustration of the above card. Here we have two regions. We have the region R and its complement. And the idea is to see how we can to connect the both sides of the black hole, right? To see how this information can be entangled. And idea, a way to do this is using the hard normal cell surface. But how we can to derive this when we're standing for uh, another gravity theories like the Horndeski gravity, and why we chose the Horndeski gravity to do this, you know. But where is the next using or considering this gravity? Okay, for our study, we considered a four-dimensional scenario using the black string. This is the same scenario used by the culture brand. Okay, but when we connect these two regions in the both sides of the black hole, we need to compute the information entangled for the regions. Uh, First, we need to know how the region R and its complement can be studied. And after, we need to see how the island can be studied and how to model the surface and the thermal entropy, because all these entropies are related. Uh, Although we compute each entropy region dependently. Okay. Uh, in the concepts of the holographic, the entanglement entropy in the conformal field theory is related to the geometry of the space-time in the dual to the secret space-time. The black hole physics implications for the entanglement entropy. We know that the entanglement entropies connect to the Bernstein-Hawking entropy of the black holes, offering a quantum perspective on gravitational thermodynamics. Where is the implication for Horndeski gravity and how the Horndeski gravity can be changed the information for these regions that are described by these entropies? These regions in the book contribute to the entanglement entropy of a boundary subregion. But the most important thing that we have, including this the Horndeski gravity, is the whole of the scalar field, because the scalar field change the entanglement entropies, leading to a rich entanglement dynamic when than the standard gravity. Okay, here is the framework, the configuration. In this configuration, we are using the idea of Takaya Mirage that provides for us in 2011 the ADS-BCSP correspondence. In this framework, we have a Lagrangian density for the gravity are in four dimensions and the boundaries are in three dimensions. And here we emphasize the importance of the geometry considerations uh, that are modified by the Lagrangian boundary density. In a schematic way, we have that this is the Horndesk Lagrange, right? And the boundary Lagrangian associated with the Horndesk gravity is this. And why we have only gamma parameter contribution for uh, for the boundary, and why we don't have contributions to the alpha parameter. This is because when we construct the boundary table for a gravity or modified gravity theory using the Takaya prescription, we consider that the boundary table have contribution associated with the Einstein tensor because the extrinsic curvature here are related with the rich tensor, and all the other terms here are related with the Einstein tensor that have uh, are related with the ridge tensor and the ridge scale, right? Okay, but when we derive and include the boundary Lagrangian here, this boundary language here increase the size of the authors, right? Because when we change the gamma parameter, we change the contribution of Horndeski gravity to the scalar field. But how are we going to derive the entanglement entities for these Lagrangians? A way to do this is using the Wald formula or Ward formulas if you prefer. But when we derive this, we can see that here we have the scalar field contribution directly, right? And change this parameter, we change the area associated, the area functional for the region R and its complement. The connection between the Horndesk gravity and the entanglement island and Hartmann surface ensure there a holograph consistency because we need that uh, the theory must be normalized. The Horndesk gravity must be still reproduce the spec unitary behavior of the page curve, providing a test for the validity of the theory. Horndesk entanglement entropy and islands. The scalar field change the geometry of the entanglement island. This leads to deviation from the standard GR predictions for the page curve and provide the constraint uh, on Horndesk gravity, right? And this is interesting because we can test the some theories when we consider extension uh, for this scenario considering the ASB safety correspondence, right? Okay, this is the entanglement entropy for the Hartmann model of surface. Here we have the contribution of the parameters through the omega parameter here. Of course, we have contributions times the geometry through the key theory. Okay, but this is changed also the island entropy, where the description of the Nash show that the entanglement entropy is the minimum of the entanglement entropy for Hartmann models in a surface and the entanglement island. For the field theory point, we tend to consider the twister operator field. In this case, we have a similar entropy in the book, but in the boundary, we have some corrections. And in these corrections here, through this term here, if this term here is equal to zero, we're back for the usual scenario described by the usual Einstein gravity in the framework of the ESBCSD correspondence, right? But the curiosity is that if the subsystem are considered larger and far from the boundary, we obtain these two entropies here in the left side and in the right side. This is a kind but theoretical residual information that given for us that if the black hole evaporates entirely from the overview point of the classical entropy, the black hole continues emit some kind of information. And if open one hole geometry as this will be responsible for the entanglement between the residual information in the left side and in the right side, and both connected by the Hartree models in the surface. And this is a shortcut about this discussion where we have that residual information that can be continued emitted by the black hole. Okay, but how we can to study the page curve, especially when we refer to study the page curve. We are talking about the possibility to study the page type and the page angle. And if you put this condition here, it's possible to derive the page type. And if you choose this another condition here, we have the page angle, both modified by Horndeski gravity, right? Okay, but what happened when we study the behavior of the page type with the Horndeski contribution? We have a competition between the entanglement island plus the Harvey-Model entanglement entropy, right? And this competition decreasing when we we change the values of the Horndeski parameter gamma, right? Okay, but we have two parameters, and you think, okay, why vary the gamma? Because alpha have no contribution for the boundary side, right? And we can fix alpha and vary the gamma. We have new interesting things about this. For example, if the page angle is have positive values, the island dominates at t equal to 0. While for negative values of the page angle, the hardening of the cell surface dominates at t equal to 0. Initially, dominate the entropy calculation to fix alpha and vary the. And this is very interesting because we have or reveal the strength of the scalar field contributions in this case. But okay, uh, if the page time, we can study the competition between this entanglement entropy. In the page angle, we can study the behavior of the page curve. In this case, the scalar field changes the internal geometry for this scenario. This is the reason that you have different behaviors of the page curve here. But uh, although these exotic behaviors, we have that the unit term is preserved in this scenario. The page time is rarely sensitive to the bipartitional point. The sensitive can be understood as a consequence of the geometry on the Hartmann of the same surface. In this case, the surface approach to zero area. The surface extending from the event horizon to any boundary points retains a non-zero area. The page type deviation degree of freedoms for small values of alpha and gamma of bipartition are limited. A scenario applicable all with the curved bottom theory. Okay. Uh, the present work that we present in the last year and was published in this year reconciled the apparent violation of the unitary in the black hole evaporation by analyzing the phase curve and modifying the elastic theory. Of course, we can test this for the other modified gravity scenarios. But why we chose the Horndeski gravity? Because not the Horndeski gravity in general, but the special truncation of the Horndeski gravity. The motivation was because this boundary theory is very special because we can see effectively the contribution of the scalar field, but have many modified gravity theories. But the question is, these modified gravity theories can be provide modifications like this. This is the question. This is an open question for me because I not test the other modified gravity theories yet. The Horndesk parameters change this curve. These changes reflect the role of the scalar field on the distribution of the quantum information, the dynamic of the black hole evaporation. This is the some work that you can be studied to see how to construct and how is the main idea behind this. The first paper is this paper uh, of the Professor Karch and the Professor Lizarralda. This is the paper that I published together with Bernard Solidowski. And this is the paper about how you can to uh, construct the Takayama theory for extending for the modified gravity theories. Okay, thanks for your attention. Thanks, Bernard, by invitation and for organizing conference every year. This is very beautiful, and for me is an honor to participate of the all conference.
Thank you very much, Professor, for the wonderful talk. Now, I think we have plenty of the time for the questions. So, is there anybody has a question here? No? Okay. I think there is no question, right? Yeah. Thank you again, Professor.
In the chat box, there is one, Professor.
Oh, there is one?
In the chat.
We have a question in the chat about the Sarah. Hello, thanks for the last talk. Does Horndeski graphic alter the location of the contact external surface? Would be inside or the outside of it? Yes, yes, this is correct. And me and Ben, we are doing a new work, construct a new work about this, because we are considering uh, this using the quantum complexity for see this in a more effective way. But yes, the Horndeski graphic altered the location of the quantum external surface. And would light be inside or the outside of the black hole? Yes, alter the both sides of the black hole. And because the book have correction for the Einstein gravity through the the Horndeski gravity, and the boundary side also have correction the two sides, and you can change both sides of the black hole. In the interior of the black hole and in the exterior of the black hole, I have a paper that I published where I explain these concepts in a more, how can I say to you, in a more pedagogical way. And I can send to you this paper, okay, if you want, of course.
Is there another question? I think we can end the session. Thank you very much, Professor, for your talk. And I think this is the end
Thanks.
of